Hello and welcome to this video tutorial on doing cluster analysis in R. So cluster analysis is a set of techniques aimed at finding patterns in data in the form of clusters. So a cluster is a set of observations or individuals which are more similar to each other than they are to individuals or observations in other clusters. So, for example, we might collect a lot of gene expression data and without really having any prior information about the structure of our data, we may perform cluster analysis to see if there are any groups of individuals which are more similar to each other, which might signify some kind of underlying biology or pattern. So we're going to start by just loading in our favorite iris dataset. And just to familiarize ourselves with it again, we just pass it to the plot function. And we see we have a data set with four continuous variables: sepal length, sepal width, petal length and petal width, and also species. So looking at this data, we can see that we have some clusters of observations of plants, and we want to be able to automatically identify these clusters and perhaps get an indication as to how many discrete clusters there are in our data set that may represent some real differences between different types of plants. So for this data set, we already know that we have three different species of iris, which we know accounts for the differences, the different clusters of observations that we see. But for the purposes of this video, we're just going to pretend that we don't know anything about the species group membership of these plants, and just perform different clustering algorithms to try and find these clusters automatically. Most of the time, if we're running cluster analysis, we won't have any indication as to group membership. But in this case, as we do, it can be quite useful to use this group membership as a sort of validation for how well our clustering algorithms are performing. So to start off with, we're going to scale our data. So remember, this just normalizes our data by subtracting the mean and dividing by the standard deviation. And so what this does is takes out any effect of our different variables being measured on different scales. So in this data set, it's not so important because I think all of our variables are measured in millimeters. But if, for example, sepal length was measured in millimeters and petal length was measured in meters, then petal length would be given much more weight or much more importance during clustering than would be given to sepal length. So not so important for this data set, but if you have data which your variables are measured on different scales, for example, it could be distances and age, then it's important to scale your data, and we simply do that with the scale function. Now, clustering algorithms are only able to cluster on continuous variables. And in our data set currently we have four continuous variables and one categorical variable, species. And so we're just going to get rid of that categorical variable by subsetting our iris data frame and saying we want all rows and all columns except column 5. And now if we take a look at our new data frame, you can see that we just have our four continuous variables and that they've been scaled, and so their values will sort of hover around 0 as they've been mean subtracted, and they're now in z-scores. Okay, so there are different algorithms for performing cluster analysis, and one isn't necessarily right for any particular data set. Different algorithms will perform better for certain kinds of data. Most of the time, it may be a case of trying different algorithms and selecting the one which gives you the best performance. So the algorithms that we're going to cover in this are K-means clustering, which is probably one of the most well-known. Hierarchical clustering, which is useful for uncovering some form of hierarchical structure in your data. And this is the kind of clustering, for example, that people often run when they run gene arrays. So you see sort of in the margins of your heat map, you may see dendrograms indicating the hierarchical clustering. And then finally, we'll talk about density-based clustering and clustering based on statistical models. So to start with, we're going to start with K-means clustering, as it's one of the most well-known and one of the most useful. So K-means clustering works by identifying K centers in your data. So K is a parameter, hyperparameter that you specify. It's the number of clusters that the algorithm will find, and it finds K means within your data. So sort of centers of data, and then for each data point looks at the distance between that point and the K-means and uses the distance to assign that point to one of K clusters. So for example, if we specify that we have 4 K-means, then our algorithm will identify 4 clusters. So we're going to call our fit object fit K, and we run the algorithm using the Kmeans function, and we supply our data frame and we tell it the value of K. So we're going to start off with 3 because we know that there are 3 species within our data set, or because otherwise we believe that there may be 3 clusters. And if we run this and call the fit K object, then R tells us that we have K-means clustering with 3 clusters of sizes 47, 53, and 50. So these are the number of observations within each cluster. We get a small table of cluster means. So the mean of sepal length for cluster 1 is 1.13, for sepal width is 0.008, so you can find the centers of each of the clusters. We get a clustering vector, so for every observation in our iris scaled data frame, this is the cluster membership that's been assigned by the algorithm. And then we get the within cluster sum of squares for each cluster. So this is a measurement of how dispersed each of our clusters are. And then this is a useful statistic, which is the sum of squares between clusters, so how well the clusters separate from each other, divided by the total sum of squares, so the total variability in the data, and this is expressed as a percentage. And so the higher, in theory, the higher this value is, the more of the variability in our data is accounted for by having assigned cluster membership to our observations. If we have a look at the structure of this fit object, we see that we can extract the cluster membership by using the $, and then the cluster variable. And so if we want to plot our original data frame but color it by the cluster membership that's been assigned by the algorithm, we simply say color by fit K $, cluster. And so this will plot this plot as we have it here of our iris data frame, but it will color each point depending on the membership within the fit K K-means clustering object that we created. And so now this is the result of the clustering algorithm, and it's done a pretty good job, at least viewing by eye. So this cluster has been assigned and colored green, and the two clusters here are colored red and black, and we can see that the algorithm has been able to identify this cluster, which separates the furthest from the other two. And then these other two clusters are sort of a little bit mixed up a little bit. So some of the species have been assigned red when they should have been black, and some have been assigned black when they should have been red. So the algorithm hasn't done a bad job, but as these two populations of iris don't separate very well, we don't have 100% accuracy based on our species variable. But so this begs the question: how do we choose the number of k of clusters to identify, and how do we evaluate the performance of the clustering algorithm? So, for example, if are there actually 3 clusters here, or are there only 2, or are there 4, or more? So, how do we choose k? Well, we can start by fitting several models, Kmeans clustering models, to our data across a range of values of k, and then assessing how they each fit. So let's initialize an empty list called k. And let's say for I in 1 to 5, the ith value in the list k is the result of Kmeans algorithm of iris scaled, and the k-means is going to be equal to I. So if you haven't gone through or come across for loops, or the for loop tutorial that I've created, have a look at that, but don't worry about this too much. Basically what this will do is iterate over the values 1 to 5, and will fit, sorry, let me change this, from 1 to 10. It'll iterate over the values of 1 to 10 and fit a k-means model for each of those values. So we'll have the k-means algorithm searching only for 1 cluster, a k-means algorithm searching for 10 clusters, and everything in between. And these will be saved to a list called k. And so if we run this and have a look at k, and let's scroll up all the way to number 1 here. So as we saw before, we get all the information from the Kmeans algorithm. So Kmeans clustering with 1 cluster, which is basically all of the observations. We can see that they're all a member of cluster 1, of course, so this isn't very useful. But what is useful is looking at this ratio between the between sum of squares and the total sum of squares. So when there's only 1 cluster, this is equal to 0, which isn't very good. If we now perform clustering with 2 different clusters, we can see that this shoots up to 63%. So now a lot of the variation in the data is being attributed or taken up by the data being in a cluster membership. When we assign 3 clusters, this increases even further to 67%, and when we assign 4 clusters, it goes to 81%. And so actually, as we add clusters, this value will continue increasing. But what we can do is plot this percentage against the number of clusters that we have. And where we see sort of a shoulder or a kink in the plot, then this is usually a pretty good indication as to how many clusters, the optimal number of clusters that we should be looking for. But I'll explain exactly what I mean by that. So let's calculate the between sum of squares divided by the total sum of squares for each k-means model. So let's initialize an empty list, and then we're going to use our handy for loop again for I in 1 to 10. The between sum of squares divided by total sum of squares at index I is going to be equal to the between sum of squares. So this is how we extract the between sum of squares for from each k-means model, divided by total sum of squares. So what this will do is for every K-means model, it will take the between sum of squares, divide it by the total sum of squares, and save it to the between sum of squares, total sum of squares list item. So if we run this, we can then plot the ratio of sum of squares against the number of clusters in our data. So plot 1 to 10, these are our cluster numbers, against our between sum of squares, total sum of squares. The type of plot is going to be equal to B, which means both, so this will draw dots and lines to connect them. And then let's just to make it more readable, our ylab is equal to the between sum of squares divided by the total sum of squares, and the xlab equals clusters, and in brackets this is k. And then if we run this, we get a plot which has the number of clusters, k, on the x-axis, and the ratio of between sum of squares to total sum of squares on the y-axis. And the way that we would interpret this is where you see a shoulder in your plot is where the optimal number of clusters is to select. Sometimes this is very clear cut. So you sort of have, going from one cluster to two clusters, you have quite a sharp leap. And then after that, it doesn't increase very much. Here, it's a little bit ambiguous as to whether we should be selecting 2 or 3 clusters, largely because those two different populations of iris overlap quite heavily. But in addition to using the sum of squares, often it's quite useful by just eyeballing your data and seeing whether the clusters that you identify by eye are being identified by the software. And so what I'm going to do is just plot the iris data set and color each individual observation by cluster membership after running 4 different K-means algorithms. So I'll say for I in 1 to 4, plot iris, and the color is equal to cluster membership from each of our K-mean models. So this will basically plot the results from looking for 1 cluster, 2 clusters, 3 clusters, and 4 clusters, so that we can sort of select by eye which we believe is the most appropriate. So it starts with the last one where we have 4 clusters, and you can see that the software has identified this red cluster, this black cluster, and this blue and green cluster. So it looks to me actually as if this is one single cluster that's being identified as 2 down here, and I don't think that reflects anything real in our data actually. If we look at 3 clusters, this looks a little bit more realistic, I think. So we have a black cluster here, a red cluster here, and a green cluster here. Obviously, these 2 clusters are overlapping. These are much more similar to each other than they are to this guy over here. I guess looking at sepal length against sepal width, they sort of separate a little bit more nicely. So this looks a little bit more real to me. And then if we drop down to 2 clusters, then again, this looks quite convincing because these 2 species of iris don't separate out very well. So you could be quite easily forgiven, I think, for accepting a 2 cluster outcome to your model as well. So I hope that you can see how to fit K-means algorithm, and that it's up to the user to select a value for K, which is a caveat in some ways, because it becomes much more subjective rather than based on your data, and that sometimes you have to pick the most appropriate value, either based on looking at the sums of squares, looking at the data yourself with your own eyes, or sort of conceptually, knowing a little bit perhaps about the data, trying to make a best guess decision. Okay, so that's K-means clustering. What about hierarchical clustering? So whereas K-means just finds fixed points in your data set and compares the distance between each observation and those fixed points, hierarchical clustering typically starts by placing each observation in its own cluster, so a cluster of one, and then it stepwise merges clusters by looking at the distances between different adjacent points. And whereas K-means takes and provides no information as to perhaps the structure that or the relationships that your observations have, hierarchical clustering gives you an idea as to whether or how not only individual points are similar to each other, but how different clusters are similar to each other. So rather than supplying the raw data frame to perform hierarchical clustering as we did for K-means, instead we have to supply what's called a distance matrix, which is a matrix of the distance between every point in your data frame to every other point. And we can generate this using the dist function. And again, we're going to supply the scaled data frame. And we're going to call our hierarchical model fit h, and the function for performing this in R is called hclust, hierarchical clustering, and the first argument is the distance matrix that we just created called D, and you can just run that as you want. We're going to supply an additional argument, which is the name of the method that we're going to use to perform the clustering. So there are different types of hierarchical clustering algorithms. By default, hclust runs one called complete linkage, which is often very good. There are other options such as single linkage, which work in certain situations but not very well in others. We're going to use one called Ward D2, which also works quite well. So again, there's no hard and fast rule as to what is right and wrong. It depends on your data. Certain data structures fit certain algorithms better. To decide which one works best for your application, it's just a case of running them both or running different algorithms and then comparing their performance. For this set of data, I know that ward.d2 works quite well. If you want to have a look at the other algorithms that are available, you can just type $hclust and have a look at the different options. And we can plot our hierarchical clustering model, which draws a nice dendrogram for us. So we can basically see from this structure that every observation is labeled at the bottom, and then each one is clustered with its most similar neighbors. And then you can see that different clusters of observation are clustered together, and as you move higher up the tree, then you have larger and larger clusters. So this is useful often if you are interested in some kind of hierarchical structure in your data. So, for example, you may have a data set containing snakes, cats, and dogs. And the snakes will cluster together, the cats will cluster together, and the dogs will cluster together. And then all the cats and dogs will cluster together, and then all of the animals will cluster together at the top. Often we are interested in some kind of structure, but in this situation we're just interested in identifying the major significant clusters in our data, as we were a second ago with the K-means clustering. And so basically it's up to us, the data scientist, to decide exactly where on this tree we're going to cut to decide where our clusters lie. So for example, if we cut at this point, we would end up with two different clusters, all of these guys and then all of these guys. If we choose to cut the tree down here, then we'd end up with three clusters, these guys, and these guys here. And the lower down the tree that we cut, the more clusters that we end up with. How we decide how many clusters to identify is very much the same as we would have done for Kmeans. So we can evaluate the sum of squares for the clusters that we identify. We can interrogate it by eye and look at the suitability of the clustering. So to visualize this cutting of the tree, we're going to use this function rect.hclust, to which we're going to supply our model, and we're going to tell it that we want 3 clusters and to color the border red. And so I hope that you can see that in order to categorize all of our observations into one of 3 clusters, we would have to cut the tree at this point, so that everything below this point is considered a cluster here, everything below this point is considered a cluster here, and everything below this point is considered a cluster here. And this also shows us exactly which observations will end up inside which cluster. To actually get the a vector of cluster membership, we have to use the cut tree function, where again we supply the clustering model and supply the number of clusters. Oops, there's only 1 t. There we go. And if we call clusters, then we get a vector of cluster membership for every observation in our iris data frame. And then we can evaluate the suitability of our clustering algorithm by plotting the iris data frame and coloring based on cluster membership from our fit-H clustering model. If we zoom into this, we can see that it does a very similar job to how the Kmeans clustering performed when we identified 3 different clusters. Again, looking at species, we can see that this species is quite easily clustered from the other 2, and these 2 species up here, although generally are clustered correctly, so for example there's a misclassified individual here, and these guys are misclassified as well. But otherwise the clustering algorithm seems to perform reasonably well. Most of the time when I'm performing clustering, either of those 2 algorithms and the variations of hierarchical clustering perform well enough for what I'm interested in doing. But there are some other, perhaps more sophisticated techniques for clustering, such as model-based clustering and density-based clustering. So let's start with model-based clustering. So we're going to use a package called mclust, model clustering, which performs clustering using this mclust function. And what this does is fits statistical models called mixture models to our data to look for different distributions in our parameter space, and then based on those distributions finds whether observations in our data set are likely to have come from the distributions that are mapped in our data. That may not make a lot of sense. Let's play around with it and see exactly how it performs. So quite simply, you just supply the scaled data frame to the mclust function. But if we call our model object, we don't really get very much information. It just tells us that it's an mclust model object, and it says that the best model was ellipsoidal varying volume, shape and orientation, VVV. So basically we'll see in a second that mclust fits several different types of models to your data, and not only picks the statistical model which best fits your data, it also picks the version of that model with the number of clusters that it thinks best explains the data, and so that this is telling us that it's basically identified 2 clusters that explain the variation in the data. But otherwise, just calling the model object doesn't give us much information. If we choose to plot this model object instead, it does this sort of strange thing where it gives us different options of plots that we can have a look at. So for example, if we want to look at the BIC, the Bayesian Information Criterion plot, then we type number 1 and hit enter, and this basically shows us the BIC plot here. So what we're looking at is on the x-axis the number of clusters that the algorithm has tried to identify. On the y-axis is the BIC, the Bayesian Information Criterion. So this is basically a measurement of how much variability is explained away in the data. So the higher this value is, in theory, the better the model is performing. These lines all represent several different, or one of several statistical models that the software has fit to your data across the different numbers of clusters. And so basically what it does is it looks at the model which performs the best, the one with the highest BIC, and which in this case is VVV, which remember is the one that it told us it was using. And it also finds the point at which adding additional clusters no longer contributes to the value of BIC, no longer contributes to explaining away the variance in the data. And so for this reason, I hope you can see that this algorithm has chosen the VVV model and has chosen 2 clusters as explaining most of the variation in our data. If we look at the classification plot, number 2, we can see that the algorithm has classified these 2 different clusters. And so unlike where we chose 3 clusters before, it's only now classified these 2 different species as a single cluster because they don't separate particularly well from each other. If we look at the uncertainty plot, this basically shows us, again, our subjects and their cluster membership, but increases the size of, or draws in large, observations for which cluster membership is uncertain. And so there's only this one subject which is it's not particularly certain as to whether it belongs in the red cluster or whether it belongs in the blue cluster. It's quite normal to have individual observations which don't fit particularly well in either cluster. If we had many uncertain points, then perhaps we might consider a different clustering approach. And then finally, we can have a look at the density plot, which may or may not be particularly useful, but this is a representation of the final model that was used to model the data. So I hope that you can see that these are 2 bivariate normal distributions that have been used to categorize each observation into one cluster or the other. So if an observation is found here, then it's going to be clustered. It's likely that it's a member of this distribution of data, and so it's more likely to be assigned to this cluster than to this cluster. Now you'll notice that unlike Kmeans and hierarchical clustering, this model-based clustering gives no flexibility to the data scientist as to the number of clusters that are identified or to how the group membership is assigned, which in one way is a good thing because it removes the subjectivity of it, but in another way is bad because it doesn't allow you to tune and select the parameters. In this case, I still think that a 3-group clustering outcome is more correct, and so if this was the data that I was trying to model, I would probably not use this model-based clustering and instead stick with hierarchical or K-means. And then finally, we'll look at a way of performing density-based clustering. And now there are lots of packages that will perform density-based clustering in one way or another in R. The way that density-based clustering works is that it identifies dense regions of observations and uses that information to assign clusters. So if an observation is in a region which is dense with observations that have already been assigned membership to one cluster, then that observation will be assigned to that cluster over another cluster. So we're going to use the package dbscan, which you can install by running this command. I'm not going to run that because I've already installed it. But once that's installed, you just need to load it into your memory by calling library dbscan. Oops. Before doing that, you need to type 0 to escape this mclust selection. There we go. Library. Okay, so we're going to fit a new model called fitD, and the function to run this density-based clustering is dbscan. We're going to supply it the iris scaled data frame. And then there are these two arguments that we need to supply, EPS and min points. So if the value of min points, if this many observations is found within the EPS distance of an individual observation, then the software will start a cluster. If this is not particularly meaningful for you, then don't worry so much about it, but there are sort of handy ways that you can define best guess parameters for best guess values for these parameters as are suggested by the authors. So min points is often the number of dimensions in your data frame plus 1. So for example, for us we have 4 different variables that we're clustering from, and so our min points value will be 5. To work out a best value for EPS, there is a function that we can use called knn distplot, and we're going to supply the iris scale data frame and say that we expect to find 3 different clusters. And so what we get is this strange looking plot, and what we're basically looking for is the elbow at the far right hand side of the plot, and the value that this corresponds to on the y-axis. To make this a little bit easier, we can add an ab line to our plot, and the horizontal line equal to 0.7, color equals red, line type equals 2. So I've just manually added this line. It's up to you to look at this scale and decide where the elbow in this plot lies. But I think this is around 0.7. And so we can substitute this in as our value for EPS. And then if we have a look at our, let's run this. And if we have a look at our density-based clustering model, so it tells us that it's performed DBS scan, 150 observations in total. These are the parameters that we supplied for it, and it's identified 2 different clusters of observations and 6 noise points. So noise points are observations which are too far away from any of the clusters that have been identified to actually be given a cluster membership. And so you can see that 48 observations are members of cluster 1, 96 are members of cluster 2, and 6 are belonging to no cluster because these are our noise points. And again, we can plot our iris data frame and color by cluster membership as indicated or as defined by our density-based clustering model. And you can see again that actually, just like our model-based clustering, this algorithm has identified two different clusters. So this population of iris separating from these two populations of iris. And so you can see that these sort of slightly more automatic methods that pick their own numbers of clusters don't do a fantastic job at separating out these two different species of iris. There are two reasons for that. One of them is that the variables, that these numeric variables for these two different populations of species are quite similar. They're more similar to each other than they are to this population, and they don't completely separate very well using any of the variables. The other problem is that really we need more observations. We need to collect measurements from more plants than are currently contained within our data frame. And if we continued sampling and increasing the number of species that we have, then you might imagine that this population begins to become more discriminated from this, or easily separated from this population. And so this is actually a concept which is a problem for clustering algorithms called the curse of dimensionality. And basically what the curse of dimensionality states is that as you increase the number of dimensions in the data frame across which you're performing your cluster analysis, the number of observations that you need within each cluster to be able to cluster different subsets of observations from each other increases exponentially. And so in this case, we're only clustering on 4 variables, which is fine. Most of our clustering algorithms are happy chewing out that many variables for the number of observations that we have. But as we go to 5, 6, 7, or as many continuous variables as you like in your data frame, the number of observations that you need to be able to adequately identify clusters needs to grow exponentially. And so in such situations where you have high dimensional data sets and you want to identify clusters, then it's usually a good idea to perform some kind of dimensionality reduction technique, such as principal components analysis, which we have gone through in one of the other videos. So for example, what we would do in this case is perform a principal components analysis to reduce these 4 dimensions into just 2, and then run our clustering algorithm on just those 2 principal components to identify our clusters. And although we won't run this now, this may result in more adequate separation of our 3 species of iris. So I hope that's a useful introduction to cluster analysis in R. The sort of takeaway message is that there are different ways of different clustering algorithms. There isn't one algorithm that is always the best. Different algorithms perform better for certain kinds of data. But what you should be doing is running separate algorithms and then evaluating how well they explain or highlight the patterns in the data.